we spent some time on studying networks, complex graphs, or spatially embedded networks with the simplest kind of distributed flows. One example is any kind of distribution networks when some material, where some stuff is transported. It can be water, it can be oil. But as far as the structure of the equations governing the flows, you can end up with the same set of equations in some approximations for the power grid. That is to keep in mind. So again, that's the common feature, that we're going to look at networks where the function of the network is to transport some abstract or some very tangible stuff. So we're going to look at cascades in these type of graphs. In particular, once I get into the bulk of the presentation, I try to make a comparison. What are the typical signatures when you look at cascades in non-spatial graphs, Erdős-Rényi complex graphs, Barabási-Albert networks, or just chaotic networks in general, and what you see when you play the same game in spatial graphs, random geometric graphs, or topology stolen from the power grid. So we mimic the same rules and carried out there. So just one motivating point, and it will be obvious at the end that why you can see such a big difference in the outcome is that very similar size triggers can lead to very different outcomes. And one example is a very recent small failure in some portion of the US power grid, happened to be in the DC area. It was a single line or single node failure, resulted in a shady maintenance work, and it was a very small scale basically. It was localized to actually to one of the districts around the White House. So even the situation room went dark for a couple of hours, but it was a very localized outage. Again, local failure, and the outage happened to remain localized. And then you can recall a much larger scale event where it was also the result of a local failure, possibly a single line damage as a result of a falling tree branch. And the result was the complete blackout of a huge chunk of the northeast. And again, it's the same network, same parts of the network. You trigger it somewhere else, but the same kind of trigger, local failure, and you can go from an outage on the scale of a few kilometers to the scale of a few thousand kilometers. Okay, so what are we going to do? What is the actual model that we're going to throw on this or that network? We're going to look at distributed flows, and interestingly enough, these type of flows were also motivated from a completely different context, just looking at betweenness centrality and information centrality as an alternative to the usual shortest path flow. And so when you look at betweenness in networks, there was a huge body of research addressing what is the betweenness when you imagine shortest path flows of information or matter between all source and target pairs. But what if the flow of matter or flow of information is not going on the shortest path? So again, you can consider distributed flows, current flows for that matter. And that's exactly what Newman and Ulrich Brandes and co-workers did a while ago, again for a completely different purpose, but it's the same kind of flows, current flows. Now, as far as the particular structure of the equations, it doesn't get any simpler than that. You look at flows in resistor networks, but the structure of the equation happens to be equivalent to the simplest DC approximation of power flows in the power grid. And so these are the kind of motivating factors that we considered and carried out our studies. And it is important to mention that there's been a lot of studies, perhaps not on complex networks, but on networks a long time ago by Sid Radner and co-workers in the 1980s, just looking at the failure sequence, the cascading events that one can initiate and carry out in spatial graphs. Those were regular bits, but the underlying phenomena is the same. You have a network with flows, you have nominal ratings of the lines, or you can assign nominal ratings for the nodes as far as the processing capability, and you just remove a line or you remove a node, then the flow is going to be redistributed according to the laws of the conservation laws that you prescribe, and see what happens. Okay, so this is exactly what we did, carried out, and again in the part of the talk I tried to go through and sort of step by step in parallel, just talking about what is the major observed difference when you look at cascades in networks with distributed flows. When you look at these, we look at networks with non-spatial characters, error chain graphs, or the same dynamics on spatial graphs, random geometric graphs, or structure taken from power grid networks. So this is the basic equation, which is just if you want to take it to the complete abstract level, just current flows, right? Voltage differences between two nodes, and it is coupled by a line which has a particular conductance value. The inverse of that would be the resistance or resistor network. Just imagine a complex graph, and each link has a resistance value, and you can put sources and targets. You can have one pair or many pairs as long as they're balanced, and see what kind of flow structure develops, and in particular what happens when you assign some nominal rating to lines or nodes, you remove them, and then what happens next. Okay, it is important to mention that the structure of current flows is completely identical to the DC approximation of power grid. That is already a huge degree of reduction of the complexity of the problem. Of course, actual power flow equations are nonlinear. It's a rather complex set of equations, and once you take it to this level, it becomes simpler, undoubtedly. But it is worthwhile to take it as a starting point. What kind of flow structure you can get out of this, and what kind of cascading failures can be initiated in this system. So the analogy is obviously complete if you associate phase differences with the voltage differences, and the power with the current, the same kind of equation. And the inverse of the coupling is the line resistance, corresponds to the line reactance. So the same kind of physical problem set up on the corresponding graph. So what we looked at, we considered the various graphs, spatial, non-spatial, and we probed this network using these conserved flow equations. We just used the sources and the target pairs, and we went through all the nodes. So in this case, if you want to make it more relevant to the power grids, of course, you have to take the list of nodes which are generators and the list of nodes which are loads. You can make it more realistic here. To keep the analogy, we just did the same. We went through all source and target pairs and essentially evaluated that what is the current load on each node and each link, and then go from there. So here is so the setup is quite simple. Conserved flows in networks, and if you want to look at them, just resistor networks, they correspond to power flows. And here is the setup of the cascade model, which is rather simple. It was put forth by Edwilson, Motter, and Inch and Bly a while ago, where you calculate your equilibrium currents to begin with. You can refer to that as a load, and then you add some tolerance. So alpha, you can think of alpha as the strengthening of your edges or of your nodes, depending what you're looking at. And the bigger the alpha, the higher the tolerance on that particular node or edge. So it's a very well-known cascade model, and a lot of network research has been carried out with this in mind, where you have some kind of flow problem, distributed or shortest path, the nodes and edges have some carrying capacity, and you calculate that at the original scenario, then you add some percentage, a relative fraction alpha on top of it. And that's important because that kind of helps that if you make some small damage locally to the network, then it may survive at a larger extent. So that's how the cascade is initiated. You remove a single node, for example, in this case initially, or you remove a single edge or a larger region. And then as a result of that, because you are building these distributed flows, then the flows are going to be. And so that's the setup, how we go from there. So what I'm going to do is I'm just going to go through some basic signatures when you put the simplest flow model on various networks, and see how they differ when you look at them on non-spatial graphs, in particular complex Hershey networks or scale-free graphs drawn from the configurational model. And I'm going to start with these because they don't have spatial features, and they do share some similarities. So we're going to look at the node removal and the node tolerance case, and this type of plot will capture the size of the surviving giant component after the cascade stops. Right from the rule, it is clear that you remove a node. In this case, we remove the node with the highest load, and as a result of that, the flow will be redistributed, and it may trigger the failure other nodes because the load goes above the rating. Even the 1 plus alpha capacity was not sufficient to tolerate the increased flow. So G is the giant component. Once the cascade stops, it's the simplest, not necessarily the only one, not maybe the best one, but it does capture what is the structural soundness of the network when all cascades stopped. So that's G, the size of giant component, and alpha is the access tolerance that we assign. So these type of curves show you that in these graphs, the more you invest, you can really alpha to the cost, right? That's how much you strengthen your nodes or edges. So the more you invest, the better off you are. Okay, so the G versus alpha curves in non-spatial networks have a monotonic feature, which is useful for any kind of planning or predictability. It's a monotonic behavior. The more you pay, the more you get. And also you can see different network realizations for Erdős-Rényi graphs and scale-free networks, and they don't differ a lot from one another. In this case, you may see 3 realizations, and they fall kind of close to each other. So it shows that there is some kind of self-averaging in these problems when you put these models with conserved flows on non-spatial graphs, Erdős-Rényi or scale-free graphs. Another interesting game that you can play in these flow problems or any kind of cascading problems is, and I show it because it again will highlight the differences between spatial and non-spatial graphs, is that the previous one, when you increase alpha, was obviously a cost-related improvement. The more you pay, the more you get. Typically higher alpha, higher tolerance to strengthen your network, we relate to the better outcome, stronger, larger G. But you can have a cost-neutral solution. And again, perhaps it was, in other contexts, it might have been mentioned earlier, but related to complex graphs, Edison Motter was the one who put this forth, again, quite a while ago, that you can have a cost-neutral solution to optimize the size of the surviving network by preemptively removing nodes. In many ways, it may be analogous to load shedding that you can actually do in the power grid, but just the philosophy is that you remove a bunch of nodes. In fact, in complex graph, they happen to be the ones with small load because there's not much to be redistributed, and it actually helps. So once the attack happens, then you remove a fraction of F nodes preemptively yourself, and you can end up with a larger value for the size of the surviving giant component. So if you take off some nodes, you can be better off, and of course it doesn't cost you anything. So it can be quite useful. And this particular graph, what it shows, 3 different network realizations, and qualitatively they are the same, and it actually happen to fall quite close to each other. So this type of behavior that I refer to in this talk as self-averaging. So you don't have to take any average over network ensemble, and if you run the same cascade scenario on different networks, you will see qualitatively similar behavior. Okay, so you can, it is useful again for planning and predictability. So self-averaging, and in the previous case, when you invest more, you get a better outcome, so monotonicity there. In this case, you can do some optimization using preemptive removal. Okay, so in the rest of the talk, I try to contrast what I've just shown. Perhaps these are the simplest observations that one can do, and it is very well known what I've shown so far. So we can repeat the same thing in network structures which are actual power grid structures, whatever is available publicly, or ensembles which perhaps closely resemble those structures. In our case, it turned out that the closest family of graphs to capture the property of power grids were random geometric graphs. Well, 2-dimensional setting and exponentially decaying degree distribution, and essentially no shortcuts. Okay, so random geometric graph and that family captures pretty much all of that. Okay, so just some flavors, what you can see and what you can observe initially when you play the same kind of cascading scenario for a grid structure. Again, distributed flows, you can call it current flows or power flows, whatever is your context, but essentially it's the most fundamental conserved flow problem where the flow is conserved at the nodes and the cascade is triggered as before, and you can assign nominal rating to the nodes or to the edges depending what you want to study, and you can start with single node failures. Okay, and this just showed all the color is not particularly useful, that removing a particular node, what is the size of the surviving giant component. Although the colors don't come out right, but I can tell you that on the periphery, usually if you remove nodes at the edge, you don't cause large damage, and somewhere in the bulk you do. But it's not particularly informative. If you do a scatter plot, you can go after perhaps the load landscape, and you start playing with the initial load of the particular node that you remove, and you indicate the surviving size of giant component. And while you may say that if you happen to remove or attack nodes with a large initial node, you're gonna cause relatively large damage, small g, but if you choose nodes with small load, you can also cause that much damage or even more. In fact, if you happen to trigger nodes with a small load, you can either end up with very large damage or very small damage. And you have this typical bimodal feature. So definitely you cannot just simply correlate the damage that one particular node removal will result into the load, although that would be a natural candidate. Okay, so let's see how they respond, how spatial graphs, random geometric graphs, and then consequently the grid structure will respond to node removals, and how it is in contrast with what we have seen before. So Erdős-Rényi and scale-free graphs, this is what I've shown before. Why? You might see some non-monotonicity and deviation from self-averaging, but that's purely the result of a small degree. So those graphs, if you start to have dense enough links, which means higher degree, higher average degree, you typically see self-averaging and monotonicity, what I referred to earlier. But in structures, spatial structures resembling the grid or the actual grid that I will show as well, even if you boost up the system and you consider relatively high degree, higher than 10 or so, you will still see a lot of fluctuations. So the point is that you definitely see that there is no self-averaging, or at least much poorer, and you would have to go possibly to much larger system sizes, which may not have much to do with actual grids. And in a given realization, you see a lot of non-monotonic fluctuations. And that's basically what it tells you, that you keep dumping money on the problem, you increase your node level or edge level tolerance, and the resulting size of surviving giant component is not going to behave monotonically. Okay, so you increase the node tolerance, and suddenly you can have a lower surviving giant component. So non-monotonicity is a clear signature of cascade problems in the grid and in spatial graphs in general. Essentially, you can see the same observation for the actual European portion of the grid. This was called the UCP grid. The same rules, same cascades. This is when we play with node level capacity and edge level capacity. And the blue curve is when the node is the largest load removed. And you can see it increases, and then one particular point you can see that as you increase the node level tolerance from 40% to 45, so basically you increase the cost that you want to protect the network, you actually ended up with a drop. So this is a common feature with these type of problems when you have distributed flows in spatial graphs. You can see the same, essentially the same behavior for edge level capacity limitation. So I can quickly show some movies corresponding to this drop, just to illustrate that what is the outcome when you actually improve your network. Supposedly, you boost up some of the tolerance, and at the end, you end up worse. So the one on the left is just the visualization of the cascade. Let's say when the nodes have 40% tolerance, and on the right, you initiate the cascade at the same node, and perhaps you can see that there is a much larger, darker region. And certain nodes are highlighted with blue. Those are the ones which happen to survive here and not here. Possibly it would have been better off if they just go down or remove them preemptively, because effectively they might have behaved, not might, but they would have behaved as fuses. So underlying the cascades and mitigating these cascades is to understand which would be the set of nodes which would act as effective fuses. And it does go back to one of the original papers that I mentioned by Redner, that these fuse networks had a very different nature of the cascades and the full understanding of how you can infer the largest damage and how you can mitigate against that. It is the understanding of which set of nodes would be fuses and how you can describe them. And we are just at the very beginning to understand those questions and those challenges. Okay, so getting back to this self-averaging or lack of self-averaging, again, I'm just gonna recap this preemptive node removal that I mentioned, again, put forth by Edgerson in non-spatial graphs. Again, the point there was that you preemptively remove a fraction of F nodes, and you see how the system responds after the cascade as far as the size of the surviving giant component. And we saw earlier that it was a nice curve which had a maximum. Well, it turns out that in this case that it's not monotonic, it fluctuates, and as you can guess, it varies from sample to sample. So there's very little self-averaging, at least for these system sizes. However, it is easy to get misguided. It turns out, in addition to the power grid structure, we also did the same game for random geometric graphs. Again, the spatial model for grid, fairly reasonable. So we did the preemptive removal, and this is what you can get, the black curve for one network realization. It's not particularly meaningful, and definitely not something that one would recommend as insight, planning or prediction. There's no particular predictability for a given graph. If you take 300 random network realization from random geometric graph and average over them, you do get this curve. But it has no use as far as telling what to do in one particular graph. Now, as far as even remotely related, you want to do some optimization, let's say, for the grid, spatial graphs, conserved flows, it's one network. So any kind of averaging over X hundred graphs is not going to have any meaning as far as prediction, predictability, and insights for how to protect the grid or how to do it better. Okay, as a small sidetrack, what I've shown so far is the contrast when you implement the simplest model with conserved flows, with on non-spatial graphs, Erdős-Rényi, scale-free, and the same game on spatial graphs, random geometric graphs, or the actual grid structure. Obviously, you can interpolate between those. One way to do that is that you take your random geometric graph, which is effectively it's a 2D spatial graph, and in a Watt-Strogatz fashion, you start rewiring the links. This way you can interpolate between a purely spatial graph to something which has shortcuts. Of course, at the far end of the spectrum, when you rewire every link, you would end up with an Erdős-Rényi graph, effectively. So P is the fraction of links that you rewire. If P is 0, you are in the RGG limit, and if you increase P, you rewire every link, you would hit the Erdős-Rényi limit. In between, you're going to have something in between, some kind of small word structure. So you can see that for small values of P, you still have a large profile of non-monotonicity. The outcome versus the investment is not going monotonically. The more you pay, doesn't guarantee a better behavior. And a lot of variation from network to network. So again, at least at these system sizes, you don't have a lot of self-averaging, which would be helpful for predictions and insights. Of course, once you start increasing P, you enter the small word regime, you do get rid of these non-monotonic features, and also the sample-to-sample fluctuations are going to be smaller. So this would be sort of the mathematical extrapolation from spatial graphs to more of a non-spatial ones. Of course, this is not much use for example, mitigating cascades in the grid, because you cannot connect with a superconducting wire California and Texas. This is what you would get if you do that. You get predictability, and actually you would have a smaller values of alpha when you saturate the system that essentially is going to be stable against any regional removal. But of course, that's science fiction. You're not going to have that type of connection bridging the two coasts of the US and thereby getting rid of fluctuations and making the saturation faster. But from a network viewpoint, this is the best, perhaps the best way to see what makes differences between spatial and non-spatial graphs. And at the single network level, there are a lot of sample-to-sample fluctuations and no monotonicity in terms of G as a function of the investment. Okay, so so far I have shown single node removal but the message can be extended for multi-node removal and variability. So what this movie shows, and this is not just the end of the snapshot, and maybe it's first slide just to look at it, is what happens when you remove 9 nodes which kind of fall into a small region. In this case, this is the small circular region, and I choose 9 nodes, but different 9 nodes. Okay, so imagine that there is an attempt, but there is some variability. Which are the 9 nodes which are taken out? A small region, but you can have different 9. It happens to be the case that in this particular region there are 12 nodes. Okay, which are the 9 nodes you take out? You don't know. Maybe there's some error in your targeting. So you get rid of 9 nodes, and you can, they're not the same 9 nodes, there may be some overlap between them, but you can see that the outcome is very different. In one case, the cascade happened to impact only a small region, and in the other case, even though it was roughly the same area, but a different 9 particular node, happened to breach the whole system and essentially impact the entire network. Again, the same model with conserved flaws, but instead of single node removal, we just multiple node removal for this type of attacking scenario. But you can see, so non-monotonicity and variability, again, second important feature. Again, third one was lack of self-averaging. So for multiple node removals, you can also now recall the sensitivity to the particular choice of nodes. Again, even though they are roughly in the same area, small variation in the target set will result in a huge variation in the actual impact. Again, this is just the simplest kind of flow that you can put on a graph. However, the structure of the flow really resembles the DC approximation of the power. Okay, multiple node removal, non-monotonicity again. The more you pay, what you get. Turns out if you increase your node level tolerance, processing capability or whatnot, you can end up worse. In this case, the blue nodes indicate the damaged ones, the ones which went down as a result of the cascade at 10% tolerance. When you add an additional 5%, so you go from 10 to 15%, at the end you ended up worse. So why? Because you by chance and accidentally happen to protect some nodes which you should not have. And again, this is a common feature in these problems where the nature of the flow is such that it gets redistributed anywhere in the system. So that's the nature of Gyorgy's law and also the power flow equations, that small disturbances anywhere in the system can have a far-reaching impact, even if only the structure is purely spatial. Okay, so before I finish, how much time do I have?
6 minutes, including questions and answers.
6 minutes?
Including questions.
So I will show something which is not particularly insightful, but it shows that there is potential. So one can do better than just kind of uniformly throwing out investment on each node or each link uniformly. And this was the curve that I showed earlier. Again, this is like signature plot. One particular graph, size of giant component once the cascade stops as a function of your investment. That's the tolerance parameter. That's what you assign to each node. And again, we did it before in a uniform manner. So every node had the same excess capacity or excess tolerance. So what we're going to do, again, just so instead of uniformly giving everyone an excess alpha, percentage-wise, we're just going to randomly add something such that the total cost will be the same. So what we're going to do is, again, a cost-neutral assignment of resources. And in the context of information system, it can be capacity allocation. And for the power grid, depending whether you protect lines or nodes, this will be the nominal rating. You have to have a better material or whatnot. And the way we do it is that at the end of the day, when we assign the local resources, the sum of those will be the same. So it's going to be a constant cost stochastic allocation of the capacities. Okay, so here is what one can see when you kind of limit the spread of your stochastic distribution of the capacities by, let's say, 25%. So you can see the broadening. Okay, so the line, what I showed before, went like this. Once you assign your capacity stochastically, you can have some improvement. If you increase your search space, you can even have a bigger improvement. For every value of the average tolerance, which still remains alpha relative to the equilibrium loads, you can have some broadening, and you can see worst case, best case, and kind of the average one in between. and at some point it will saturate, but clearly shows that, for example, when instead of having, in the case when the capacity allocation was uniformly 40%, and we were somewhere here, now that we allow stochastic allocation of the resources, you can have a worst case scenario, or you can have the bad one, even without understanding why that is the bad. I can just take that allocation and use that for my network. So there is potential in this network, and you can certainly do some stochastic search or perhaps exhaustive search, depending on your computational resources. And whether with or without insight, you will be able to produce a network and an allocation of capacities which will do better. It can actually do significantly better. Instead of 30% survival, you can end up with a network which has a 40% survival or whatnot. And definitely you can mitigate the fact that previously from 40% capacity to 45, there was a drop. But once you include these random search, you can do better in all cases. So again, one may criticize the lack of insight, and that's absolutely true. So we were unable to come up with a clear heuristic solution to the problem where I can assign a single node measure at the beginning of the problem, and I can figure out which are the nodes that I want to protect more and which are the nodes what I want to protect less. But what our results show is that there is no simple measure which can help you understand which are the locations that you have to strengthen and which are the locations that you should not defend at all. In fact, treat them as fuses, shut them down. So it would be nice to have something like that, heuristics or something rigorous perhaps, but unlike in other networks, non-spatial graphs, where you can get away with a lot of heuristics, single node load measure degree, and you can say a lot about what kind of damage the removal of that node cause, or what kind of additional capacity that node will require. When you look at these type of flows on spatial graphs, there are very little insights that you can find along the way. So that's sort of the main finding. So again, because of this broadening, you can identify which is the best case scenario. So you can, at the end, you can end up with a network which is more optimal than the one that you started off. Okay. And you can see the same scenario. I will just show these movies, and then I will just finish off with a few remarks. So again, as a result of this random search, it turns out, again, the blue nodes indicate the damage. So you can end up with a scenario when the size of the damage is smaller than in the worst case, and the one in the middle would be somewhere in between. Okay. So getting back to one more word about predictability, is it easy to relate which are the nodes which receive a larger amount of resources? Well, it's not easy. This is, for example, the load indicated on the horizontal axis and the excess capacity relative to the equilibrium currents, and there is no particular structure. So definitely it doesn't make a lot of sense to say that nodes with a high load should receive this or that much extra capacity. There is no structure in here. So I would say that there is no simple node level or edge level measure that you can sort of manufacture at the beginning of your studies and predict that which will be the set of nodes that you want to defend more than the others. So, 2 words before I finish. So I started off with the simplest model, again, models with conserved flows, and you can relate it to information flows in some networks, but because of the exact mapping between current flows and the power flows, it really is the fundamental model for the dynamics which happens in the grid. And if you want to get a little bit more realistic, these are the papers that I recommend by Zussman and co-workers, where they look at also the DC approximation, but with actual ratings and with actual line capacitance values and all that. But the main finding is pretty much the same, that localized damages can result in far-reaching outages. This is the case for the US. So it is very different than what you would see in percolation models or any kind of models where if you implement it on a spatial graph, the spread is going to be local, and if you have no shortcuts, then in a few steps, the cascade is not going to spread beyond those few steps. It turns out that in the grid, where there are no shortcuts, you can have a damage which is going to spread arbitrarily far away from the initial point within a few steps. So this is how the outages are shown with red line after 5 steps, even though the hop length in this particular network is probably 15 or 20 steps. So this is a very typical character of these graphs, that non-local spread of damages because of the nature of the flows. Another point that I want to make before finish is that, that obviously what I showed is just the beginning to understand how cascades are happening. And I assume that when you proceed with the cascade, there is a balancing somehow. Well, in real grids, it doesn't happen for free. The grid has to be balanced, otherwise the whole set of equations are going to break down and you're going to have transients and all that. So you have to do a balancing, which means it's almost a necessity to have a communication network on top of the grid. So this would be the case of an interdependent network. And there have been many nice works recently or not so recently, basically starting this new line of studies, cascading failures in interdependent networks. One of the first ones considered percolation. And the message was that cascades in such scenario can be catastrophic. Another one followed up, relied on senpai dynamics, and it showed that it can be optimized. So you can mitigate the cascades with some level of interconnections. But perhaps the third one is the one that I would recommend if you are interested in the grid, where they use real power flows and some minimalistic dynamics, what the communication network would do on top of it. So I think this is the one that is as simple as you can get. So the equations are still DC approximations, and it uses the simplest toy model for a computation network whose role is to control the grid. And that's the point. If you couple networks, you have to consider what their function is. They do not operate in vacuum, but one network carries some flows, and the other one ensures balancing and which nodes to shut down, etc., and whether or not there is a backup power or not. So this is a very nice work. And it really has I think the main features at the minimum level that you should have to understand what is the nature of flows in a coupled network, where one network carries flows, happens to be the grid, and the other one's role is to control that flow. Okay, so I think I'm done with that. I pointed out the three main points that you can see in spatial graphs: lack of self-averaging, lack of monotonicity as far as the investment and the outcome. So those are important points. Also variability. If you have multi-node attacks, so there's no way to tell that if you make a small change in the target area, whether or not the outcome will be similar. I will just finish with this. I would like to thank my collaborators, students, postdocs, and Polak, who's actually sitting here. So Noemi, Ala is also here, and Shin, Andrea, Samik, and this is where I stop. So if you have some questions, I'm happy to answer.
Thank you very much for this very interesting talk. Questions, comments, remarks? Please.
So how did you choose the input node and the output?
Excellent question. I did not. So what I showed earlier, actually, and the bulk of the talk was that we just followed exactly the same averaging process that I averaged over all source and target pairs. So as far as giving prediction for the grid, where you have given set of generators and loads, forget about it, okay? It was just a toy model. So this way, I just assumed that each node is equally likely to be source and target. Now, if you want to do a real prediction for the grid, of course, then you go and see what is available in the data. When we did back then, we just didn't have that particular richness of the data. But now we have, for the UCT network, we do have the given set of loads and generators. So you can go back and you fix those just like your network, and you don't change that. And what you have to do in every step of the cascade, what we got free for here, is that you have to do a balancing. So we didn't do that. So it's almost like a more optimistic scenario than it really is. So.
No other questions. Thank you very much once more.